Hi, I'm Taylor Bart,
And my name is Colin Weinstein.
and we were sponsored by the CAOE Center, and we worked on the passenger arrival analyzer. Our sponsors were Dr. Jorge Sever and Dr. Ronald Askin, and our technical advisor was Andre Larson.
The basics of our project are that we had to utilize YOLO, which is an object detection algorithm that stands for You Only Look Once, in order to count new passenger arrivals at the airport using CCTV footage. Andre, our technical advisor, provided to us an existing project with requirements to improve its accuracy and efficiency. Additionally, due to the development of COVID-19 and its drastic impact on the airport industry, we were tasked with being able to identify changes in passenger behavior due to COVID.
At the beginning of our summer semester, we had an initial meeting with our sponsor, and we were able to define the project motivations. It was to be able to predict or to produce a predictive model that modeled the behaviors of the passengers as they arrived in the new arrival terminal. This would be able to reduce the overhead and manpower required to count these new arrivals, and it would be able to prepare and aid management to make decisions on resource allocation, such as where to put security at any of the terminals in the airport. And to be able to, one of the main problems is to be able to reduce the error between the manual and algorithm counts, because we were provided a manual count over the course of a day, and we were given what the algorithm could originally count. And so to be able to reduce the error between these two would provide a more reliable forecasting of passenger behavior. And more precisely, there was lanes of pre-check, clear, and just general, where they would want to know the individual lanes that passengers were going into.
During the customer discovery process, we discussed with the customer the exact pain points that are being experienced with the existing algorithm. As explained, the current algorithm has difficulty identifying overlapping individuals accurately. This is demonstrated in the image below, where only 2 detections are made within the red box, despite there being 4 to 5 passengers within it. Furthermore, the customer wants to reduce overcounting due to stuttering and double counting. Additionally, the customer has no control over camera angles, which sometimes change during the middle of the footage, as well as the fact that the customer may wish to perform the algorithm on various terminals. A robust algorithm is required in order to perform accurately with all these conditions. Finally, security that stand in the front of the lanes, boxed in blue in the image below, constantly move back and forth over the thresholds to count how many passengers enter those lanes. This leads to massive overcounting in these lanes.
So after being shown the initial conditions of what we were expected to solve, we were given the technologies that we used to solve this. They were already using TensorFlow with Yellow V3, and we did some research in the beginning to see if there was other technologies we would want to implement, but none shown enough of an accuracy increase to warrant completely switching up the project that we inherited. And so we just made the assumption that fine tuning would yield more improvements than porting to a completely new project. So, like I said earlier, the justifications was that most of this we already had inherited, and the sponsor had more of an emphasis on improving the current technologies and what was already developed. And so then, uh, when we were researching, we wanted to make sure though that YOLO was conclusively what we'd want, and it was much better suited for this than the RCNN and some of the faster and fast versions of the RCNN. There was also a tiny version of Yellow V3, but even though this allowed us to run much faster, which we would later solve, it turned out to be widely inaccurate, and so we stuck with the normal Yellow V3 algorithm.
After much research, we were able to settle on a few design details for the project. First off, by fine-tuning some of the existing person detection algorithms parameters, we were able to get initial improvements of the count provided by the algorithm. Some of these parameters included modifying the interval over union threshold, the score threshold, and the anchor boxes used to determine the IOU for each detection. Additionally, by fine-tuning the person detection algorithm by annotating footage provided by the customer, we can train the algorithm to better detect people in the CCTV footage. Furthermore, as requested by the customer, we can use the footage to create a data set for detecting heads, carry-ons, and any other objects that they would wish to for improving the algorithm. Finally, we wish to design an automated system to determine the ideal parameters for algorithm setup, as these parameters may vary depending on the terminal and any additional training that the customer does on the algorithm. The justifications for our design decisions stem from the fact that our customer's highest priority is to create an accurate count of the passengers' arrivals. Fine-tuning the algorithm will provide reasonable improvements to the accuracy while not requiring much time for fine-tuning. While head counting may prove more accurate than counting bodies due to the occlusion of bodies in lots of the video segments, the time that it will take to train and create the custom data set for detecting heads as well as any other objects that the customer wants us to detect will take so long that it is lower priority. Finally, due to the fact that the ideal parameters will vary depending on the terminals and with any new training done, having a automatic testing process is crucial so that the customer is able to modify the algorithm to be most efficient in the future.
So the main deliverable that the sponsor wanted was suggestions and methods for improving the detection algorithm's accuracy. And so we came up with the three main suggestions of bird's eye view as preferred camera angle to be able to better isolate and identify individuals in large crowds, especially in a terminal where you could have up to 20 to 50 to even 100 people on the same screen of footage. And so then we were also working on the IOU and score thresholds where we wanted to make it dynamic to where based on the size of these crowds, where it's sparse or more crowded, you can change it to better identify individuals by themselves or individuals among a crowd. And lastly, we came up with a way to run on every second, fourth, eighth, and even 16th frame to reduce runtimes without losing accuracy. And here's a graph showing it wasn't exactly a one-to-one improvement where if you were to read every other frame, you don't necessarily get twice the speed up. Where if you look at this graph, if you read 1-1, that's a one-to-one ratio. You read every frame, where 1-2 is then reading every other frame, and 1/8 was reading every eighth frame. But this is all based on ratios, and we could see that the 1/8 frame rate, or 1/8 of the frames that had to be read, was able to speed up the algorithm over 4 times. And this improved speeds where some of these needed 10 to 12 hours to process on the GPU, where now we could process multiple videos in that same time in 2 or 3 hours, which gave us a lot better ability to test other hypotheses that we were coming up with. And so here's a video side by side of all 4 of them running, and you can see that in the faster ones, it actually reduced some of the stuttering that we would see in videos. The top left is the normal time. The second top right is the second fastest going half time. The bottom left is going at a 4th rate, and the bottom right was going at 8 times speed, meaning that it read every 8th frame. But most importantly, even with this improved runtime, we weren't losing accuracy.
From these results, the value that we've created for our customer is mostly economic and social. As for the economic value, providing an automatic count reduces the manpower required to obtain these counts and allows for precise scheduling to ensure efficient workflow at TSA and other areas of the airport. Additionally, the improvements that we've made to execution times drastically reduces the cost of resources to the customer by allowing them to run the algorithm in real time or faster. The social benefit is due to two things. Firstly, by improving the efficiency and speed of checkpoints at TSA, passengers won't spend 30+ minutes in line, and thus the public perception of TSA and traveling by airports will improve. Secondly, understanding changes to passenger behavior due to COVID-19 allows the customer to predict any long-term changes that may be necessary.
So after this semester, some of the lessons we learned is that there's a lot of data, and the analysis of it takes as long sometimes as getting the data itself. Instead of in the beginning where we had the frames and we had to manually find the counts for each of the lanes and the totals and put it into a CSV, a lot of this can be automated and done as the video is being processed. Another point is that at the beginning of this, we had only one GPU between us. We were able to get another GPU machine built to test on this, but without that GPU, the video processing was taking so long that it would take a week to process a 2-hour video. And so that kind of leads to the last point, which is why we came up with the frame skip to see if it wouldn't reduce accuracy, is because as we were going through this project, we realized the speed of testing was directly correlated to speed of development. And as we were able to improve it a couple magnitudes in testing, we were starting to see a lot more improvement in regards to development. And so our future development plans will consist of filtering unnecessary classes that could be slowing down the data set to improve the testing speed even further, extracting those frames and annotating with FOT. This is where we can make our own training sets and we can annotate it with this FOT software. Further analysis of the IOU and score threshold still needs to be done, but it needs to be improved. So the automating analysis of the IOU and score thresholds. And then we have some other stuff that we want to test out, such as the k-means algorithm for determining ideal anchor boxes, which determines the width and the height of these boxes and what they should ideally be. And lastly, we need to train and detect on new footage that was given to us because the passenger's behavior has changed due to COVID-19.